Welcome to the 23rd lecture of graph theory. So, today we are going to introduce a graph class called perfect graphs. The motivation for introducing this graph class is the following inequality, which we have already seen. So, we know that for every graph chi of g, the chromatic number of the graph is greater than or equal to omega of g, where omega of g is the size of the maximum clique, number of vertices in the maximum clique in G. The inequality is very trivial because each vertex in a clique has to get a different color. So many colors should be present. Now, the question is it the reason for chromatic number to be high? We had asked this question. We have seen that it is not true. We had constructed graphs which is triangle free, but the chromatic number is arbitrary high, and we had mentioned that we can even ask the shortest cycle in the graph be greater than some number k, given number k, and still the chromatic number can go arbitrarily high, right. So, chromatic number being high has nothing to do with the presence of a large clique in the graph, though the presence of a large clique can in fact make the chromatic number higher than that, higher than equal to that. On the other hand, even if the clique number omega of g is quite small for the graph, the chromatic number can be high. So, naturally this question arises, for what kind of graphs can we say that this inequality becomes equality? That means this kind of graphs. Does it make sense to study the kind of graphs where chromatic number is equal to omega, the clique number? As such, it does not make much sense, because you can take any graph with chromatic number of g is equal to say k, and then what you do is, so this is the graph g, and then you put a small clique here k here on k vertices, right. So, then you say that, see, here is a graph see h, where g h is equal to g union k k, right. The clique number will be k k and the chromatic number will be equal to k. So, we can't tell anything about the structure of this h, because g is an arbitrary graph. In fact, it is as good as asking what is the structure of the graph with chromatic number k, because the structure, just that we have this clique here, we can't tell much about the structure of g, because g is any graph, it can be any graph with chromatic number k. So, as such this question cannot make sense. So, we have to define the question or ask the question in such a way that this kind of bad examples does not come. So, Claude Birch formulated the following question. He asked, so consider the graphs such that not only for the graph itself, for every induced subgraph of it, say h is an induced subgraph of g, h is then suppose it happens that chi of h equal to omega of h, not only for, so this also includes, this is for all h, right, such that it is an induced subgraph of g. Suppose this inequality holds, not only for, remember that is not only for g, it is also for every subgraph. In that case, he called that these graphs can be called perfect graphs. He named them perfect graphs. So, a perfect graph is a graph such that every induced subgraph of it has the property that its chromatic number is equal to clique number. So, so if this is the class of perfect graphs as he defined, right. So, graph G is perfect if chi of h is equal to omega of h for every induced subgraph h of G. Now, he asked, can we characterize these things, can we understand this kind of graphs. So, the first question is, we know that all graphs cannot be perfect, like we have seen that there are graphs whose chromatic number is much higher than its omega. So, and also the definition looks a little bit cooked up, because as we mentioned, if we had just asked I want omega is equal to clique chromatic number for the entire graph, it would not have made much sense. Therefore, he had to introduce this extra concept that every induced subgraph also has this property. So, it looks like a little cooked up, but still it so happens that there are several graph classes, graphs, in fact graph classes themselves, which are well studied graph classes, which happens to be perfect graphs. So, we will see some examples, right. So, so for instance, let us look at the following. There are several examples. From the next slide I will show. See, I have listed around 10 classes which comes under the class of perfect graphs. Maybe the most important among them can be bipartite graph, because that is probably the most well known, and we know it very well, right, bipartite graphs. So, two colorable graphs. So, what do we need? We want we will check whether it is a perfect graph or not. We have to verify all these things are perfect graphs. So, why do we say that they are perfect graphs? That is because so you need this property that the chromatic number is equal to omega for every induced subgraph. Now, you take an induced subgraph, it is again a bipartite graph. One good thing about bipartite graphs is that if you take an induced subgraph, it is again a bipartite graph. Now, we can verify it whether omega is equal to chi for any bipartite graph, then it would show that any bipartite graph is perfect, right. So, the crucial property is that if you take an induced subgraph of a bipartite graph, it is again bipartite. Therefore, if you verify that for a bipartite graph chromatic number is equal to omega, that is enough. Chromatic number is equal to clique number, that is enough. Now, for a bipartite graph, the value of chi, right, so it can be of case 1. If it is 1, then it is just a collection of isolated vertices, and omega is definitely 1 there is nothing to worry. So, let us say chi of G is equal to 2, and we know that in a bipartite graph the biggest clique is just an edge, there is no triangle in it, there is an edge in it, otherwise it will not be 2, chromatic number will not be 2. So, the chromatic omega equal to 2. So, it is trivial, right, for bipartite graphs, the trivial examples of perfect graphs. So, though it looks like it is cooked up, the entire class of bipartite graphs happen to be perfect graphs. So, it is not so bad, right, it can capture a lot of graphs. Now, let us look at the complements of bipartite graph, that is a little more non-trivial. So, complements of bipartite graph, that means a graph whose complement is a bipartite graph. Let us say G is such a graph. Can I show that chi of h is equal to omega of h for every induced subgraph h of such a G? Again, we do not have to worry about every induced subgraph, because if you take an induced subgraph of the complement of bipartite graph, it is again, because if you restrict our attention on that vertices on which we took the induced subgraph, the corresponding complement will again be a bipartite. Therefore, it will again be a complement of a bipartite graph. So, induced subgraph retain the property. So, we need not worry about all the induced subgraphs. So, we can just prove that if G is a complement of a bipartite graph, then it satisfies the property that the chromatic number equal to clique number for that, omega, biggest clique size for that. to show this thing, we should first understand what is the chromatic number of such a graph. So, now if I look at the chromatic number of this graph, what will it correspond to for its complement, which happens to be a bipartite graph? See, essentially the chromatic number, that is the number of colors required to color the vertices of the graph, is the number of independent sets to cover all the vertices of the graph, number of independent sets, because each color class corresponds to an independent set and each vertex of the graph belongs to one of the colors classes. That is what essentially the chromatic number is, the minimum number of colors to color the graph, the vertices of the graph. That means the minimum number of independent sets required, so that this collection of independent set cover all the vertices of the graph. So, the same question in the complement will be the minimum number of cliques, complete graphs, because an independent set graph set here will become a clique in the complement. An independent set will become a clique. Therefore, we are asking for the minimum number of cliques to cover the entire vertex set of a bipartite graph. This is an easy question for bipartite graph, because you see in a bipartite graph we do not even have a 3 clique, the biggest clique is only 2 edge. So, what do we do? If you want to minimize the number of cliques to cover the bipartite graph, we will of course pick up the biggest matching, right, because we want to collect as many edges as possible, so that they are independent. That means they do not touch each other, right, they do not share anything. So, that will give us the matching number, if you remember, alpha dash of G, right. So, matching number, biggest independent set, so alpha dash of G, right. Biggest, the CCC, remember alpha was the notation for independent set, alpha dash the corresponding edge version of that, right. So, alpha dash of G. Now, this, but then this may not cover the entire vertex set, because it may not have a perfect matching, its maximum matching may not cover all the vertex set. So, how many more we have to take? Now, because the edge, no more edge can be taken, so we have to take vertices, individual singleton vertices. So, we have to take the one for each remaining vertex, that n minus 2 into alpha dash of G. This is essentially n minus alpha dash of G. How much is this? You remember the conics theorem, where we showed that alpha dash of G is essentially the vertex cover, right, MVC, n minus, we called it beta of G, right, is not it, beta of G, and this is essentially alpha of G. And alpha of G happens to be the alpha of its omega of its complement, because we are talking about the complement graph, right. So, the complement graphs omega. So, we are talking about the complement of a bipartite graph. In the bipartite graph, its clique number will become the independent set number, that we have seen that in that corresponds to the clique cover number, that means the minimum number of cliques required to cover the vertex set of the bipartite graph, which happens to be the chromatic number of the complement of the bipartite graph, right. So, we got that for the complement of the bipartite graph, chi and omega are equal. So, essentially we see that this question of whether the chromatic number for the complement of a bipartite graph is equal to the clique number translate to conics theorem, namely the vertex cover is equal to the matching. So, though through a small translation, so we are using it to prove this thing, right, in the corresponding bipartite graph, right. Now, we go to the next one. So, we have shown that bipartite graph are perfect, in fact, their complements are also perfect graphs. Now, here is another one, line graphs of bipartite graphs. So, what do we mean by line graph? So, we have seen the line graph many times before. So, when we studied the edge, the connectivity, we had introduced the line graphs. Line graphs means this given a graph, we are constructing another graph where the edge set of this given graph will be the vertex set, edge set will become the vertex set, and two vertices will be made adjacent there if the corresponding edges in this original graph are touching each other, are incident with each other, are coinciding on one vertex, right. So, this is called the line graph. Now, we are saying if you take the line graph of a bipartite graph, that is going to be perfect. Why is it perfect? Again, we do not have to worry about every possible induced subgraph, because if you take an induced subgraph, this essentially corresponds to some edges of the bipartite, some selected edges of the bipartite graph. So, it is line graph. So, again it is another the line graph of another graph which is a line graph of some other bipartite, some smaller bipartite graph. So, if we prove that for any line graph of a bipartite graph chi is equal to omega, that is enough as usual, right. So, our intention would be to prove now that for line graph of a bipartite graph, the chromatic number and the independent set number is chromatic number and clique number is equal. What is the clique number of the line graph of a bipartite graph? Of course, the clique in the line graph should correspond to the edges incident on the same vertex, right, because this is going to be, if in the original graph we have something like this is going to be the clique, these vertices corresponding to these edges will become the clique in the line graph. So, unless we have a triangular structure, but triangles are not there in bipartite graphs, right. So, therefore, we can see that this things in fact which correspond to the maximum degree delta, right. So, if you can select the vertex of maximum degree, say delta is the maximum degree, that will correspond to the omega of the line graph of G, right, because G being a bipartite graph. Now, we ask, okay, if this is the omega, then what is the chi of L of G, chi of the line graph of this thing? Chi here is going to be so we want to color the edge set of the so the line graph is to be colored, that means the vertex of the line graph correspond to an edge of the original bipartite graph. Therefore, the coloring the vertex set in the line graph correspond to coloring the edge set of the bipartite graph, such that no two adjacent edges get the same color, right, where in the line graph if we say no two vertices which are adjacent get the same color, correspondingly we mean that in the original bipartite graph from where the line graph was constructed, we want the edges to be colored in such a way that two adjacent edges get different colors. That is essentially we are asking for a proper edge coloring of the bipartite graph. Again, another theorem of conic. So, we had studied earlier that the minimum number of colors required to properly edge color a bipartite graph is essentially delta, that is a type 1 graph, right. Delta is equal to the chi dash of G, and which is essentially chi of L of G. So, we have delta for chi of L of G, delta for omega of G. So, the line graph of a bipartite graph also satisfies the condition for perfect graphs. So, the line graph of bipartite graph is also perfect. Now, again we look at the complement of here I made a mistake, complements of the line graphs of bipartite graphs, complements of the line graphs of bipartite graph. Are they also perfect? As usual, we can again argue that the induced subgraphs you need not worry, because induced subgraphs themselves will be some complement of some line graph of a bipartite graph. So, we will just show that if a graph is the complement of the line graph of a bipartite graph, then it will satisfy the chromatic number is equal to clique number equality. So, what is the chromatic number of the complement of the line graph of a bipartite graph? Essentially, it will be the clique cover number, as we mentioned in the last case when we studied the complements of bipartite graph. Essentially, the color number of colors to color the vertices is essentially the number of independent sets to cover the vertex set. So, when you go back to the complement, then we took the complement of the line graph. So, when you go back to that line graph, we see that correspond to the clique cover number. That means the minimum number of cliques required to cover the line graph of the bipartite graph, right. And now, what is the omega here? Omega, that means the clique number of the complement of the line graph will become the independent set, the biggest independent set, right. Clique number will become the stability number, namely the biggest independent set size for the line graph. So, for the line graph, if you are talking about the biggest independent set, what will be that in the corresponding bipartite graph? Because of course, the vertices are edges of this graph. So, in the independent set will correspond to the biggest matching, that will become alpha dash of G for the original bipartite graph. See, if G is the original bipartite graph, this will be the biggest independent set in L of G, and that will be omega of L of G bar complement. This is what we are interested. So, that is essentially this alpha of L of G, and that is essentially alpha dash of G, right, the biggest matching in the maximum matching in the original bipartite. Now, what is the chromatic number of L of G bar? Essentially, that is the clique cover number. I can use K for that, K of L of G, right. Clique cover number, as we have seen, each clique of the line graph of the bipartite graph correspond to a vertex, the incident edges on a vertex, the collection of incident edges on a vertex in the original graph. So, essentially we are seeking, and the vertex set is essentially the edge set of the original bipartite graph. Essentially we are seeking some vertices, a collection of vertices from the original graph, such that every edge is incident on one of them, right. So, what was that? That was, we are very familiar with it, that is essentially the vertex cover, right, which we used to call beta of G, right. Minimum vertex cover is what we are seeking. So, the minimum vertex cover of the original bipartite graph will be the clique cover number of the line graph of it, and that will be the chromatic number of the complement of it. So, this one is going to be beta of G, right, and this one alpha, this omega is going to be alpha dash of G. We know that alpha dash of G and beta dash of G are equal again by Koenig's theorem. So, it is we see that if a graph is the complement of the line graph of a bipartite graph, it has to satisfy the equality that its chromatic number equal to its clique number, right. Chromatic number is equal to its clique number, that is what it is. So, therefore, they are also perfect graphs. So, we have seen bipartite graphs, their complements, line graphs of bipartite graph, their complements. Now, here is a different category, the so called comparability graphs. So, what are comparability graphs? The comparability graphs are certain graphs defined from partial orders. So, you remember what is a partial order? There is a base set universe, and then we have some relations on some relation defined on the set. So, set is essentially, it can be U, and then essentially a relation is a subset of u cross u, right. So, it's a Cartesian products. We can draw it by directed edges, whatever the relations are, we can draw it by directed edges like this. This can be the relation, whatever is the what do we say partially, when do we say it is a partially ordered set? We need three properties. One is this reflexivity, that means a vertex is related to itself, a comma a belong to R, right, something should be, and the other is symmetry, that means sorry anti-symmetric, that means if AB is element of R, then BA should not be element of R unless A and B are equal. So, which means that when you draw, if you draw this arrow from this vertex to this vertex, we should not draw the reverse arrow also, right, that is what. So, if you are trying to represent it using a directed graph, the relation is a directed graph. Now, the third property is more important, which is namely the transitivity. Suppose AB belongs to the relation and BC belongs to the relation, then we need AC also in the relation, right. So, for instance, if AB we put a directed edge here and BC we put a directed edge, then we should have this one AC and also this direction should be like this, right. This is what the AC should be in this thing. This is the transitivity. If all the three properties are satisfied, it is called a partially ordered. So, now we can also ask the question. So, suppose you are given a partially ordered set, or maybe we can construct a graph out of it like this, directed graph out of it. Now, we can delete the direction from that, right, and also we can get rid of the self loops, because they do not make much sense for us, because then we are interested in simple graphs, we can anyway they are trivial. So, we get rid of those things and then we take down the underlying graph after deleting the directions, underlying undirected graph, deleting the directions, and yeah. So, such a graph is the graph, the comparability graph corresponding to the partial order, the comparability graph of the partial order. In other words, there will be an edge between two vertices if those corresponding elements in the partial order are comparable. They belongs to the relation AB. AB will have an edge, either AB or BA is in the relation, right. Both cannot be, one of them, right. So, if one of them belongs to the relation, see if they are comparable, right. Then we can, of course, once we define a comparability graph of a partially ordered set. So, a natural question which comes is this. So, okay, so there are certain graphs which arises from a partial order like this. You first constructed a directed graph from the partial order, deleted the self loops, deleted the arrows, that means directions are forgotten, then the underlying simple graph is called the comparability graph of the partial order. Now, given an undirected graph, do we can always ask this question, given some undirected graph, do we have a corresponding partial order for that, right. What does it mean? It means that could I have got this graph from some partial order by this procedure? Sometimes it may be possible, sometimes it may not be possible. For instance, can we think of some graph for which, so for instance, suppose I draw this graph. So, is it possible that I can get a partial order from some partial order, so that this is the graph of that, underlying comparability graph of that? It is actually, we have to somehow try to recreate those arrows here. So, for instance, suppose the arrow was like this, then suppose the arrow was like this. Now, we are lost, because this cannot be the correct direction, because if this was, see, this is A, this is B, AB was in the relation and BC was also in the relation. Transitivity says that we should have this also, but this is not there here, this and with this arrow, this is not there. So, we have to be careful when we try to give the directions. this direction has to be like this, because if this is this, it has to be like this. That means then we are not bothered. A B and C B, the transitivity requirement does not trouble us now, right. So, A B B C would trouble us, but A B C B will not trouble us. Now, here naturally then this has to be directed back outward now, right. Similarly, this is to be directed inward now, right. So, we can add A D and also C D. A D and C D also can be directed outward and inward, that is it. So, here we could create an orientation for the arrows such that they are transitive, the transitivity property satisfied. Of course, antisymmetry property is anyway satisfied, and now if you add all these things, we would recreate the partial order like this. So, now if you add all these self loops also and write down them as pairs, right, that relation will be a partial order, because here antisymmetry, reflexivity and transitivity is satisfied, but need not be always possible. For instance, sometimes we are forced to select the arrows in such a way that finally we will end up with a contradiction. For instance, suppose you look at this graph 1 2 3 4 5, this 5. Now, suppose I take this direction for this arrow. Naturally, as I mentioned, you cannot give this direction now, because yes, look here, this look, this edge is not there. If you take this thing, the transitivity will be broken. So, therefore, this is not possible. So, we can only give a direction like this. So, now this requirement is not there. Now, once you give this direction, as we know, we can only give this direction. The other way we will have this problem, right. Again the same problem, this is not there, therefore, transitivity will be violated. Similarly, now this has to be given this direction and this has to be given this direction, but now here we have a problem. See, this is looking like this and this is looking like this. So, now what will you do? So, if you reverse it, all the arrows will be reversed. Here anyway we got into a contradiction. So, if you had selected this area, we are forced to select this arrow like this, and then we are selecting this thing, then we this edge has to come, right, this edge with this direction has to come, that is not there. So, it is a contradiction. As we can see that this will happen for all odd cycles, odd induced cycles, right, as long as this edge is not there. If there is an odd induced cycle in the graph, we cannot give arrows consistently, right. Transitive orientation, it is called transitive orientation, is not possible. So, the question now is which are the graphs which can be given a transitive orientation. It is equivalent to asking that which are the class of graphs, undirected graphs, which could have come from some partial order, right, which could have become the comparability graph of some partial. We will just say that the class of graphs, undirected graphs, which can be transitively oriented, that means which can be seen as the comparability graph of some partial order as a comparability graph. There is a class of graphs called comparability graphs. Now, our question is, so are comparability graphs perfect? So, as we can see, if you are given a comparability graph and if you consider its induced subgraph, if you are given a comparability graph and if you consider its induced subgraph, naturally they are also comparability graph. Why? Because if you can transitively orient the entire graph, the same transitive orientation will work for an induced subgraph also. So, if a graph is comparability graph, any induced subgraph of it is also comparability graph. So, therefore, we do not have to worry the complicated condition about the induced subgraph. We just have to show that any comparability graph, the property that chi is equal to omega, that means the chromatic number is equal to clique number is valid. That is all we have to verify to prove that comparability graphs are perfect. Now, let us see what does it mean, what is chi here, what is chi of g here, and what is omega of g here. As we can see, omega of g is the biggest clique number, right. So, the biggest clique number, biggest clique size. So, essentially we just have to show that, see, we know that omega of g is less than equal to chi of g. Now, if you show a coloring which uses only omega of g number of colors, then it means that omega of g equal to chi of g, right. So, that is what we are going to do now. We will show a coloring such that the number of colors used is only omega of g. Now, we should also understand what is this omega of g in a comparability graph. It is the maximum clique, but any clique, because it is transitively oriented, you know that if you look at the directions given to the edges inside the clique, they will not form any cycles, right, directed cycles, because it is transitively oriented. It is not possible to have it. So, naturally it should be acyclic, and so there should be an ordering of the vertices, then it corresponds to a total ordering, in fact within the partial order. So, we get a subset which is totally ordered with respect to that relation, right. Any two, if you take, there is a direction between the arrows between, there is an edge and there is a direction between them. So, naturally we can do a topological sort on that, and we get a from the lowest to the highest in that, that is a total order there, right. So, we say that is a totally ordered subsets of a partially ordered set is said as a chain. It is a chain in the, it is a chain of the partial order. We have seen it when we studied the Dilworth's theorem long time ago. When we studied the Galai-Milgram theorem, we have seen how Dilworth's theorem about partial ordered sets follows from Galai-Milgram theorem, right. So, we know what is chain, what is anti-chain and all, right, chain and all. So, chain, essentially the chain of a partial order correspond to the clique. Essentially the clique or the comparability graph correspond to the corresponding partial order, the chain, a chain in the corresponding partial order, and similarly a chain in the partial order will become a clique in the comparability graph. It is very obvious, because a chain means everything is related with each other, every pair is related with is part of the relation, therefore, those edges will be there. So, that will become a clique. Now, so we can consider this coloring. Here is the way to color now. So, for every word, we have seen it in the Galai-Roy theorem also, this technique. So, what we do is we took we can take a vertex, and you can look at the, say, Galai-Roy theorem, we were looking at the so we can look at the biggest chain that is starting from there, right. Among the chains which are starting here and going further, you can look at which is the biggest chain. The number of vertices in that can be given as the color of this color, this with the number of vertices in the biggest chain. Now, everything gets, so of course, now we are going to claim that this is a proper coloring. If this is a proper coloring, we are done, because we have only used with the biggest color we have used only correspond to or less than equal to the biggest length of a chain in this graph, and the biggest length of a chain is only the clique number. So, it is going to be less than equal to clique number. It cannot be less than clique number if it is a proper coloring, because we know the clique number is going to be lower bound for the chromatic number. So, it can only be greater than or equal to. So, if you want somehow demonstrate that this is indeed a valid proper coloring, then the number of colors used will be less than equal to the biggest chain, that is the clique number. So, it has to be equal to the clique number, that is the biggest chain. So, is it a proper coloring? Suppose not, then there should be an edge where some edge like this, say, right, some edge like this where right. So, the edge, if the edge direction can be like this, then we see. So, okay. So, that means this also got the same color, this also got the same color, that is why our contradiction is. Now, why did this guy get the same color as this? Here this was the biggest chain starting from here. Here definitely there is a chain starting with this green edge and then following this, right. This is one more than this, he should have got a bigger number. So, that is a contradiction. And of course, if the direction was the other way, suppose the direction was like this, then we would follow, we would consider the biggest chain starting from this, and this is the length of this will be the color of this person, and this person's color will be one more than this, at least they cannot be equal, right. So, therefore, we see that it is a proper coloring, and it follows that since we have only used the length of the maximum chain as the biggest color here. So, the chromatic number is going to be less than equal to the omega, but it cannot be strictly less. So, it has to be equal. So, that is what. So, what we have now shown is any comparability graph also satisfy the property that chromatic number is equal to omega, and because the induced subgraphs are indeed again comparability graphs, we get that the comparability graphs are perfect, right. The next one is co-comparability graph, namely the complements of comparability graphs. So, every time we are considering a class, we are also considering its complement, because this will become useful later, because we every time we see that for a class, when we see that it is perfect, its complement is also happening to be a perfect, the complement is also perfect. So, there should be a reason for this thing, we will explore it later. So, there is a general reason for this thing. So, later when we prove the general theorems, all this will get connected in one general statement, right. So, what about co-comparability graphs? The co-comparability graphs means essentially the complements of this thing. So, again we ask what is chi there. So, I will say chi of g bar, chi there and omega of g bar. What is that? This omega of g bar is alpha of g, right, the independent set number. This is essentially the clique cover number of g. So, we can just ask what does it mean. So, alpha of g in the comparability graph, essentially the independent set. So, the pairwise non-comparable elements, they are what? We have seen it before, that is called anti-chain. In the partial order terminology it is known, it is essentially the independent set, that is all, but we used to call it an anti-chain, right. When we studied Dilworth's theorem, we had called it anti-chain, right, biggest anti-chain, maximum anti-chain. Now, this one, each clique being a chain, the collection of cliques which cover the entire vertices, that is a chain cover in the terminology of the partial orders, chain cover. We are the minimum number of chains to cover the elements of the partial order. This is exactly what Dilworth's theorem considered, the minimum number of chains to cover the elements of the partial order and the biggest anti-chain. Dilworth's theorem had told that these two things are equal, right. Essentially, therefore, these two things are equal, chi of g bar is equal to omega of g bar. So, we are back to the Dilworth's theorem when you consider the complement of the comparability graphs. There chi and omega correspond to the two parameters which Dilworth's theorem told us are equal. So, complements of comparability graphs are also perfect. And now, the next one, we will look at a very well known class of graphs called interval graphs. Interval graphs are very well known and also useful in many practical situations, and essentially they are defined like this. So, to define an interval graph, so we need the real line, Now, an interval in the real line, so we take closed intervals for convenience, so can be marked like this, right. So, now suppose I have several intervals, a family of intervals in the real line, I just take several colors for this thing, right, family of intervals in the real line, these are several intervals, right. Like this, maybe, yeah, there is another one here, right, a family of intervals. Now, we see that we can get a graph out of it in the following way. So, now I am putting these vertices here yellow and now here green. So, these are essentially corresponding to the red interval, I put a red vertex, corresponding to the green interval I put a green vertex, corresponding to the yellow interval I put a yellow vertex. Now, I connect the vertices together in using the following rule. If two intervals intersect, for instance, here yellow and red are intersecting, therefore, I will put a connection between them, and green and red are intersecting, green and blue are intersecting, green and this dark green are intersecting, right, and then this yellow and red are intersecting, yellow and blue are intersecting, and this are intersecting, right, but this and yellow and this are not intersecting, therefore, I am not. This is an interval. Now, of course, this yellow and green is also intersecting. This is the interval graph. This is the interval graph corresponding to the family of intervals here, right. So, essentially we say that this is the intersection graph of this family of intervals which I have drawn here. What do I mean by intersection graphs? So, you can, so it is a more general concept than interval graphs. Essentially, you can have a universe, and let us say these are some subsets S1, S2, S3, right, S4, etc., which I have selected from the universe. So, U, right, some subset of is Si is a subset of U, that is all. Now, we can ask S1 and S2, do they have any element in common? Is there an element here and here, some X here and some here, common element? In that case, so I will introduce a vertex corresponding to each of these subsets, and then if there is an intersection between S1 and S2, I will put an edge. If there is no intersection, if they are disjoint, then I will not put an edge. For instance, S1, if S1 intersection S3 equal to phi, then there will not be any edge here, this edge will not be. But on the other hand, if S1 intersection S4 happens to be non-empty, then we will put an edge here, right. So, the graph resulting from such intersection pattern, right, is called the intersection graph of this family S1, S2, X3, etc., family of subsets of U, right. So, here in the case of interval graphs, here U is the real line, the universe is the real line itself, the real line, and the subsets S1, S2, S3, etc., are these intervals, right, they are subsets of points, right. And now, whenever there is an intersection between them, we are putting an edge between the corresponding vertices, that is all. So, therefore, we can say that the interval graphs or the intersection graphs of a family of some family of intervals on the real line. So, now see, we can always, like in the case of comparability graph, we have defined interval graphs using a set of a family of intervals on the interval. Now, it is possible that you are given a graph first, an undirected graph first, you can ask, is it an interval graph? What does it mean? It means that can we draw a collection of intervals corresponding to the vertex set of the graphs? We can say that for this vertex this is the interval, this vertex this is the interval, like that we can we get a mapping between the vertex set of the G and to some family of intervals on the real line, such that G happens to be the intersection graph of that family of interval graphs. Is it possible to construct such a family of intervals corresponding to G? This is what we ask when we ask whether G is an interval graph. If it can be constructed, then we say that G is an interval graph, otherwise G is not an interval graph. So, it is a very natural thing to ask, are there graphs which are not interval graphs, or is it possible that for every graph we can get an interval representation. Of course, every graph we cannot get an interval representation. Quickly we can see whether this graph, so this is a 4 cycle, can it get an interval representation. So, naturally, so for instance this vertex, suppose it has an interval. So, I mark it with red, yellow, green and then violet, right. So, this red, suppose I give this red, suppose I give this interval. So, arbitrarily I give this interval, then that blue I give, say just intuitive argument, suppose blue I give an interval, it has to intersect with it, right, suppose like this. Now, you can draw it in this direction or this direction. Can it draw it completely inside red? No, because then where will I put violet? Because if I draw this yellow completely inside red, then what will happen when I put violet? Violet will have to touch yellow, but then it will automatically touch red also, which is not allowed because there is no edge here. So, the blue has to come out of the red, that is very clear, right. So, the yellow has to come out of the red. So, it is essentially it should be either like this or either like this, some other. So, without loss of generality, let us say like this. Now, once I have to draw violet without touching red, so and touching red like that, we cannot put violet totally inside yellow as we mentioned before. So, we cannot draw violet to this direction, violet will have to be drawn in this direction now, right. Now, we are stuck for green. What will happen to the green? Because the green it has to touch violet, it has to touch red, but it should not touch yellow. Is it possible to draw like that? Of course, a little non-rigorous argument. So, but you can see that it is not possible. So, but I will encourage the students to come up with a very rigorous argument for this thing. But you see, this graph cannot be converted to a family of interval graphs such that this becomes the intersection graph of that, right. So, therefore, you see there are graphs which are not interval graphs. So, the class of graphs, undirected graphs, such that we can map the vertices of it to the real line, to intervals on the real line, so that this becomes the intersection graph of that family of intervals, is called an interval graph. Now, we will our intention now is to see whether interval graphs are perfect graphs or not, right. So, to see whether interval graphs are perfect graphs or not, we again have to see whether chi of g, what is chi of g, what is omega of g here, right. Now, you see again like in all the previous cases we discussed, we do not have to worry about all the induced subgraph, because the induced subgraph themselves will be interval graphs, because the vertices will correspond to some interval, we delete the other intervals, we still get an intersection pattern for that. So, therefore, induced subgraph of an interval graph is again an interval graph. So, we just have to show that chi of g is equal to omega of g if g is an interval graph, and that will show that they are perfect graphs, right. So, now is it true? What is omega of g? It is a clique. Now, when you say that clique, how will they look in the interval representation? So, each vertex corresponding to the clique has an interval and they intersect, right, pairwise intersect. Now, in a collection of intervals, if any pair has an intersection, then we can say that there is a common intersection also. This is called the Helly property of the interval graphs. So, we can try it like, so for instance, suppose here there is an interval, there is another interval here, there is another interval here. So, there is another interval here. Now, what my condition is, every pair of intervals should intersect. Now, can you see that there is going to be a common intersection point? It is not very difficult, right. because among these so I scan from these. So, for instance, I can see that any two of them, if you take, this is the intersection point of the two, right. Now, the third one cannot be see, it cannot start, we cannot have an interval like this, because if I put an interval like this, then because this interval ends here. So, this will not cut with this, right. So, it has to start before this, right, and then but then can it end, for instance, this any interval, can it end before this point? In that case, it will not cut it. So, everything will have to go into this. So, we will get a common intersection for all the three of them, and then we can refine this argument to say that there should be a common intersection part for all the intervals which take part in the clique, right. So, there will be a common intersection part, and a point from this common intersection part is such that they belong to all the intervals which take part in the clique. So, that is called so that can be taken as a point which represent the clique. That means, any point, any clique correspond to some point in the, we can associate some point to a given clique in the interval graph. Why? Because in this the property of this point will be that this point will belong to all the intervals corresponding to the vertices of that clique. So, so essentially that is the nature of this omega in the interval graphs, right. Now, we have to understand what is the nature of chi, and then we have to show that both of them are equal. That we will do in the next class. So, our intention here is to study several such classes and then show that, see, this perfect graphs, though the definition happens to be a little contrived, a little cooked up. So, though but it is not like that, several important special classes of graphs fall in this category. So, that we will do in the next class. Thank you.